Good evening and hello guys. This is Anisuzzaman from Physics Department. Once again, I comes to giving lecture about this in thermodynamics. And today I'm going to discuss about one of the sides of the thermodynamics is Carnot cycle. I'm going to discuss about the primary thinking about this. And then I go for a very nice CQ questions regarding that. So before going to the thermodynamics about the Carnot cycle, I am talking about if I go through this in a CQ questions, I need to be clear some of things regarding the isothermal process and adiabatic process. In the isothermal process, what we have learned in the isothermal process, we said in the system, the heat is need to be constant. If you provided the heat from the outer side, if the heat is getting down, then heat need to be constant since all the time. So yeah, from the first law of the thermodynamics, what we have learned from the isothermal process, first law of thermodynamics, dq equal to internal energy du plus dw. If you provide the heat in a system, some of it is going to be increases the internal energy and rest of the energy for the work done. So in the isothermal process, there is a constant heat is supplied, so there is no internal energy is changes, so du equal to 0 in this case. So all the heat we have provided in the system is going through dq equal to dw. Is it clear? Yep. In the isothermal process, we need to know some of the key points. Some of the key points which is very helpful to us, that if you know that some of the key points which is very easier to us to do any of the problems that comes related to the Carnot cycle or any other problems which is that if you find out the efficiency or anything regarding the isothermal or adiabatic process, the key points we need to be remember. So in the isothermal process, it always follows the Boyle's law, where you know that its temperature is constant, the pressure is a reciprocally proportional to the volume of it. So we know that in the Boyle's law, PV equal to constant. Okay, clear everybody? So we can write it down, P1 V1 equal to P2 V2. Be careful, you need to be remembered that only Boyle's law used in isothermal process. Okay, and in the isothermal process, once more thing is, here is the temperature is in a, there is no change in temperature, so the delta is, we need to write it down, is 0. And isothermal process, the work done is, we can write it down, the work done is W equal to nRT ln V2 by V1 if the your volume is changes between the V2 and V1, because pressure and volume is only works in the isothermal process. W equal to nRT. R is universal gas constant, we know 8.31 joule mole inverse Kelvin inverse. Temperature is whatever is given, and in its number of moles is a monatomic, diatomic, whatever they will be provided in this stem. Okay, these three things we need to be remembered about the isothermal process. And another things is for this an adiabatic process. In the adiabatic process, what we have seen, in the adiabatic process, the temperature, the heat is going inside the systems and none of the heat comes out the system. So here's a heat is inside the system, and outside the system there is no provided heat in here. So we can write in an adiabatic process in dq equal to 0. So from the first law of the thermodynamics, we can write it down 0 equal to du plus dw. So what is coming in? dw equal to minus du. So where is the minus? The negative work done. The negative work done is system is getting to cooler down. Sometimes the very 2 number or B number CQ is coming in. Why is the you write it down negative work done in adiabatic process? Because the system is cooled down. There's no heat in exchange from the inside the system and outside the system. So you can understand it very easily. That's a very nice thing. In this case, dq equal to 0, but in the temperature changes is dt is not 0. Okay, because the temperature might be cooled down and anything will be happening this side. So here we see that accepts the follows the three principles or laws in here, other laws all over the laws in here, which is number 1, remember, is P1 V1 gamma P2 B2 gamma. Number 2 T1 B1 gamma minus 1 T2 B2 gamma minus 1. And in another case is number 3 T1 B1 1 minus gamma divided by gamma T2 B2 1 minus gamma divided by gamma. This the relations comes from this Boyle's pressure's law and other laws, which is combinedly work together. We get this types of relation. It's a quite hectic work, but it would be very simple to find out that. But it's a very special notation in here is gamma. Gamma is the ratio of a specific heat of a constant pressure. That is, gamma is our specific heat of constant volume, Cp by Cv, what we have written. Okay. So yeah, molar specific heat in constant pressure and Cv molar specific heat in constant volume. And the gamma is varies in the three types of gas. One is the monoatomic gas. Number 1, do you see that? Yes. For monoatomic, gamma is 1.67. For diatomic, gamma is 1.40, and for polyatomic, gamma is the value of 1.33. So remember, what types of gas is provided in the system, that will be most important. Is it in a monoatomic, either NO, something like that, diatomic N2O2, or polyatomic carbon dioxide, sodium sulfide, something, whatever they're given is a polyatomic gases, is 1.33. So the value of the gamma, you need to be 3 things in memory. An adiabatic process, you know, there's a gamma is coming in every stage. So the adiabatic, if you do any sum related to adiabatic, you need to use this one, because it's the most important to know that. And another thing, write down the entropy in here, because an entropy comes in the system. Even in the system, if you provide the heat, there is something is not disordered system, it will be increases. This is known as entropy. We know that. Do you see that? Yeah, entropy. Entropy, we can write it as ds equal to dq by t. So why write in the entropy changes is the isothermal process, because in adiabatic process, we know the dq equal to 0, because there's no change in entropy in adiabatic process, only the isothermal process there is entropy. We can always find out. Now we see that one of the problem is clear, everybody. Okay, you put several times and need to be, I think this concept is very much important, because when you do some of the related these types of math. Now I do one of the very standard CQ, which is coming in these sides. Yeah, pretty clear. See that? Yes. In these types of maths, we see that the source temperature of a Carnot engine is 700 Kelvin. Okay, and from the graph of PV, we see that B2 is to B1. They given that we know the A point B1, P1, B2, P2, B3, B3, B4, P4, 6 is to 1, B3, B2. B4 is to B1, 3 is to 1. So in this graph, what we have family in a Carnot engine, there is in a isothermal expansion, iso expansion. This is adiabatic expansion. Clear? This is isocontraction. Isocontraction, and that one is adiabatic contraction. Adiabatic contraction. Okay. Understand that? Isothermal expansion, and this line is adiabatic expansions. There is the isothermal contractions. This is the adiabatic contractions. And what they said, that calculate the entropy in each stage, where the initial entropy is 500 joule per Kelvin is provided at a point A. Okay, the entropy you need to be measured in each stage. Okay, understand? And also point A, there is a given that the 500 joule per Kelvin entropy is provided, and from the results draw your temperature versus entropy graph. Okay, very complicated thinking as well. Okay, no worries about that. So if you find out the entropy, we need to find out, we know the ds equal to dq by t, so we need to find out the work done in each stages of. Yeah, so we can start. from this isothermal expansions in the AB stage. They said that isothermal expansions, okay, yeah, isothermal expansions, we know that the isothermal formula we have learned about from the previous sections. Then sorry, because the isothermal formula is work done, we know that in W equal to work done equal to nRT ln B2 by B1. Oh, okay, this is coming in isothermal expansion in this case. So we can write it down, the isothermal expansions, and this is a lot of pages to need to be reshuffled. Oh, sorry. So W1 equal to nRT1 ln B2 by B1. So I need to, guys, this video I need to go faster, so you need to go through very quick. There is a 2 diatomic gas. They said this is they use the diatomic gas in this engine. So the value of N is 2, R is, we know that 8.31, clear, and time T1 is temperature is 700 Kelvin into ln B2 by B1. Where is the ratios? The B2 by B1, we see that B2 by B1 is the ratios of 1 by 6, so 6 divided by 1. So W1 is comes to maybe, let's go through the calculator. You see, 2 into 8.31, you see that, yeah, 700. Oh, sorry, 821 into 700 into ln 6. Okay, so it's come 20845.32. Yes, 20845.32. So okay, now we change in entropy. We know this, ds equal to dq by t, isn't it? You see that? Yeah. So we know that dq equal to du plus dw by t. We know this in a isothermal processes there is a du equal to 0, so we find it only dw by t. So the value of the dw is 20845.32, and temperature is, you see, the 700, that is joule per Kelvin. Here this comes in 29.78 joule per Kelvin. Okay, so the total entropy at a B point, total entropy at B point. Well, what's this comes to? Because the initial entropy is provided to A is 500 and is 29.78 is added in here, joule per Kelvin. You see that? So it's coming 529.78 joule per Kelvin. Here is. Now we go through in a BC point. So whatever we have seen the BC point, so we can keep this sequence of font that we see that very clearly. Okay, so in a BC point, BC is in a adiabatic. We know the BC is adiabatic expansions. So at the BC points, there is no change in entropy because dq is 0, no change in entropy. Because dq equal to 0, so we can write in a C points the entropy comes in same at point C. So entropy comes in that S3, we can write it down 529.78 joule per Kelvin. Now CD points is again is a adiabatic isothermal contractions in a CD point. So there is also changes work done in here. So CD points we can write it down, W2 equal to nR T2 ln B4 by B3 because the volume changes for B4 by B3. Okay, B4 by B3. But where is get the T2 temperature? Oh, there's a problem. We need to find out the T2 temperature at anyhow, because we can use the one of the formula in a adiabatic process. So T1 B1. You see that? Yeah. T1 B1 comma minus 1 equal to T2 B2 comma minus 1. So we can write it down is T2 equal to T1 into B2 by B1 comma minus 1. T1 is, we know, the 700, B2 by B1. So B2 is 3 times of B1. There is a B2, and T1 is working in temperature B2 by B3. Okay, so B2 not B2 by B3, B3 by B2 temperature. So it would be B3, it would be B2 temperature. So here's the ratios, then a B by thrice B. Do you see it in here from the stem? Okay, B2 by B3. So gamma is 1.4 minus 1, because the value of gamma is 1.4 in this case. So it is then 451 Kelvin. Clear, guys? There's the temperature, how to is an exchange in here. So we find it the T2 temperature is 451 Kelvin. Alright then. Yes. If you have any queries and any problem, just ask me, because you need to be very careful when you are doing this type of math, because where to where changes. Okay, you don't write in the B2 B1, so B3 B2. You write it properly, then you can do it correct way. So we can put W2 in here. Okay, yeah. So under W2 we can write it down 2 into R into 8.31 into T2 temperature is 451 ln. B4 by B3 is changes this to, we know, B4 by B3 6 by 1. Okay, so 1 divided by 6, so ln 1 by 6 in here. If you do this type of in a calculation, because you need to be done a calculator, and it comes in it comes in minus 13430.352. Clear about, guys? Yep. So what is there is a change in entropy. In this case, there is a del S prime or the S prime. We need to write it down. So dq by dt. There is a dq is in a really context to, we know that dw, because is the dq is not present here. So dq equal to dw, we can write it down minus 1.13430.35, and T2 will have 490.51 temperature. So we can write it down, and rest the things is alright. My page is going to that, and sometimes noise 29.78 joule per Kelvin. Clear? Okay, so in the S4 point, you see that S4 point. So in a D point, we can write it down. The entropy is there coming in S4 equal to 529. We need to be plus in this one, because it's 529.78 minus 29.78. So how it is case in a 78 in here, only 500 joule per Kelvin is coming in this size. Okay, you find that very easy, done. And now we draw the graphs now with what we have found in this entropy. So we write it down, what the temperatures and where we gauge everything. Okay, so in a 700 Kelvin temperature, so what it gave, if you see the temperature versus entropy, then 700 Kelvin temperature, we find it 500 joule per Kelvin entropy, and again 700 Kelvin, we find it 529.78. You see that? Yeah, clear. Yeah. Again the 451 degree temperature, we found it 529.78, and 451, we get in a 500 Kelvin temperature. Okay, If we draw the graph like that, is temperature versus entropy, then temperature is, we say only two temperatures is theoretical, no, it's about the 451 degree and is a 700 degree Kelvin. And take the entropy here is a 500, here is a 529, sorry, 529.78. So 451 with this 25 is a 451 get 529 and 500, and 700 we also get 500 and 529. So this looks to be like in square box or rectangular, whatever you say. Yeah, entropy versus time graph is like that, entropy versus temperature. So this is the done. Yeah, this is the ECQ. It's very easy. You can go through the process. The process is very easy process, which is go through and discharge of entropy coming. I think if you understand this one well, then we get answers what the efficiency related maths is coming in thermodynamics or any other maths is oriented adiabatic process or isothermal process, or they say to be work done, find out the work done, or the change in entropy, where is the efficiency of the maths. Okay, then anything is will be completed. So no worries, first year, intermediate, and the second year. No worries, you have an abundance of time, not a great deal of time. Then we practice more at home. Thank you very much. Thank you everybody.